This is lesson 6.1. This is lesson 6.1, graphing exponential growth and decay. So the exponential parent function looks like f of x equals b to the power of x. Now if b is greater than 1, then the function is exponential growth and is increasing. If b is less than 1, the function is an exponential decay and is decreasing. Now an asymptote is a line which the graph gets close to but never crosses. So these red lines are asymptotes, and we see these green lines on the graph. It'll approach those, it'll get close to those, but it'll never cross it. So let's do some examples with the parent function. So we'll make a table with x and y values, and we'll start from 0 and get to the sides. So when f of x is 0, or when x is 0, f of x is equal to 2 to the power of 0. Anything raised to the power of 0 is 1, so y is 1. So we're at 0, 1. Now we can go 1 unit to the right and 1 unit to the left. When f of x is equal to 1, when x is equal to 1, f of x is equal to 2 to the power of 1, which is 2. When x is equal to negative 1, 2 raised to the power of negative 1 is 1/2. So we have 2 and 1/2. So 0, 1, 1, 2, and negative 1 is 1/2. So we can draw out this shape, and we see that it's increasing because the b value here, if b is greater than 1, then it'll increase, and 2 is greater than 1. So the domain here is all of the x values, and that's going to be all real numbers. And the range, y has to be greater than 0, because it's moving up here, and it'll never go below 0. So the end behavior, as x approaches, or as x moves towards positive infinity this way, f of x moves towards positive infinity. It's moving up. And as x moves towards negative infinity, so it's moving all the way to the left, f of x will approach 0. It's going this way at 0. The y-intercept is at 0, 1. We see it crosses the y-intercept at this point, and the asymptote is y equals 0. For the second example, we see that the value of b is greater than 1, so this is an exponential growth. So we know that as if it moves towards the right, the graph will move up towards infinity. And the domain is all real numbers. So let's graph some points. And negative 1, 0, and positive 1. So when x is negative 1, 3 raised to the power of negative 1 is 1/3. When x equals 1, 3 raised to the power of 1 is 3. So we'll plot the points here at 1/3, 1, and 3. We'll sketch this line. And once again, we see as x moves towards negative infinity, so it moves this way, f of x will approach 0. So the asymptote is y equals 0. And the y-intercept, where it crosses the y-axis, is at 0, 1. And the range is all the y values above 0. Now here are examples of exponential decay. So these values of b are less than 1. So when the b value is less than 1 and we have a decay, as x moves towards positive infinity, f of x is going to move towards 0. And as x moves towards negative infinity, f of x is going to move towards infinity. Because this time it's going from infinity from the left side and decreasing to 0 on the right. The domain is all real numbers, and the range is going to be y is greater than 0. We can plot these points with a table and reference values of -1, 0, and 1. So when x is equal to -1, 1/2 raised to the power of -1 is 2. When x equals +1, 1/2 raised to the power of 1 is 1/2. So when y equals -1, so when x equals -1, the y value is at 2. When x equals 0, the y value is at 1. When x equals 1, the y value is 1/2. So it'll create a shape like this. And we see here the y-intercept is at 0, 1 here, and the asymptotes, so y equals 0. So once again, the graph does not go below y equals 0, so the range has to be all values of y above 0. And we can see the end behavior is true here. As x moves towards positive infinity, so it moves this way, f of x approaches 0, so that's here. And as x moves in the opposite direction towards the left, f of x moves up towards positive infinity. Another example of exponential decay. We have our x and our y values, 1, 0, -1. Anything raised to the power of 0 is always 1. So we have x equals 1 equals 2/3. And when x so the domain is all real numbers, and the range is y is greater than 0. The end behavior, as x moves towards positive infinity, f of x moves towards 0. As x moves all the way to the left or towards negative infinity, f of x goes up to positive infinity. The y-intercept is at 0, 1, and the asymptotes are y equals 0. Here are some transformations for exponential functions. So h is the horizontal shift. If it's negative, it'll shift to the right, and if it's positive, it'll shift to the left. K is the vertical shift. Positive shifts up, and negative shifts down. If a is negative, then the function is reflected across the x-axis. If the absolute value of a is greater than 1, it represents a vertical stretch. If the absolute value of a is greater than 0, but still less than 1, it represents a vertical compression. So for these examples, we'll identify the parent function and then describe the transformations. Here the parent function is f of x is equal to 3x. And the transformations is that there's a shift horizontally. And the transformation here is that there's a shift vertically up 5. You see that here in this part of the expression. The parent function of this is f of x equals 1/2. The parent function is f of x equals 1/4 to the power of x. We see that there's a vertical stretch by 2, indicated by this a value, and a shift horizontally to the right by 1. That's indicated by this h value here. The parent function here is 4/3 raised to the power of x. There's a reflection, as there's a negative a value. This reflection is over the x-axis. There's a shift to the left by 2, indicated by this h value. And there's a shift up by 7, indicated by this k value. The parent function here is 5 to the power of x. There's a vertical compression by a half, indicated by this a value here. You know that it's a compression because the value is less than 1, but still greater than 0. It'll shift right by 4, indicated by that h value, and down by 2, indicated by this k value. So the transformations are pretty straightforward, as long as we're familiar with the general expression. So here are 2 examples using transformations. We'll start with a set of x values and some y. So when x equals -1, 0, and 1, we'll be able to find the general shape of the graph. So when x equals -1, f of x equal to 1/2 times 3 to the power of -1 plus 1. So that simplifies to 1 2/3. Zero, we take 1/2 times 3 to the power of 0, which is 1/2. When f of x, when x equals 1, 1/2 times 3 to the power of 1 is 3/2 plus 1 equals 5/2, or 2 1/2. So we can plot these points. So we have 0, so we have 0 and 1.5. We have 1 and 2.5, and -1 and 1 2/3. So we see the general direction that this graph is heading in. So thus domain is all real numbers. All x values are valid. And we see that the range has to be above 1. Normally, the range of the parent function of b to the power of x, the range has to be greater than 0. It has to be greater than 1. So our k value here will actually tell us the range as well as the asymptote. It'll also tell us the end behavior and the y-intercept here is at 0, 1.5. So for the last example, we'll set up a chart. We'll set up a table with reference values to start. So we have 3/2 to the power of -1 minus 4 minus 5. I'm using a calculator for this. We get -4.8. So when x equals -1, y equals negative 4.8. It's about here. Equals 0. We have 3 over 2 to the power of negative 4 minus 5. This equals negative 4.8. Okay, I'll get another sig fig over here. This is 8.7. 0, 4.8. These points are very close together. Three over 2 to the power of negative 3 minus 5 equals negative 4.7. So just a little above that. So regardless, we know that the domain is going to be all real numbers, and the range has to be greater than negative 5. The end behavior as x moves towards positive infinity, f of x moves towards positive infinity. As x moves towards negative infinity, f of x moves to negative 5. The y-intercept is at 0, negative 4.80. This point here, and the asymptotes